So let's pass another half hour with weird stuff, unusual stuff, little known stuff, or fun stuff together with Christoph Henkelmann. Give him a hand.
Hey. Well, thank you, and welcome to my hopefully entertaining keynote to a cabinet of deep learning curiosities. Short intro, Sebastian just did this for me. I have a deep learning company, and we work for various clients, and we encounter very weird things in reality. Haters will say this image is AI generated. Yeah, we do deep learning projects, and as such, in the real world, we encounter very, very weird stuff. So let's show you some of the stuff we encountered out there on our voyages. A little primer who maybe has not heard, some of you maybe don't know the term, a chamber of curiosities, or in German what we call a Wunderkammer. They were precursors to what we today call a museum, but the difference was that they are just weird jumbles of everything that somehow was curious or strange and found, and people would pay good money for these artifacts and display them. And it was more an entertaining and to serve curiosity and inspire people. And I like the last quote from Wikipedia: social devices to establish and uphold rank in society. So let's see how I establish and uphold my rank in the ML society today. Before we get into the details, a little warning about what I'm about to show you, as you heard from the abstract. All this is, I hope, the most important thing is that you all have fun and are inspired. I hope I will achieve that. Some of the stuff can be useful, but maybe you see something and say, hey, that's cool, I want to try that. What's really important about everything I'm going to show you, always start with best practices first. There's a reason they're called best practices. Everything, most of what we hear is not best practice. And just because it worked for me, much of this is stuff that it helped us in a very tight spot, and just because it worked for me doesn't mean it worked for you, and just because it's clever doesn't mean it's smart. So, and the final note, I think we hear this a lot in all talks these days, but it's really important. The normal solution for all your problems is more and better data. You cannot, sometimes you get away with it, as I'm going to show you, but normally you can't. So let's make sure, oh, I didn't start the clock, so let's make sure I'm not out of time at the end and you get your coffee. So I didn't I'm not here to show you only one chamber, but I brought even 7. And unlike the original chambers, I sorted them a bit, so we get some overview. And we will start with the first chamber, which I call the extra-normative chamber. We will visit things that are used not in the way that they are supposed to be used. So, given a little task, which is we want to detect treasure maps. We don't only want to detect treasure maps, but we want to display treasure maps, photos of treasure maps, so they are nice and square and can be used. This is called rectification, which means you have some rectangular object or some object and there's a perspective warping and you want to show it, you want to rectify it. And just to show you the proper solution, if you ever have to do that, you use something called a UNet. And the UNet can produce these black and white images, which show you where the object is. Then you have a nice outline of the object, and then you do some math, and you get a rectified version. This is the standard version, how you should use it if you properly want to rectify it. Detection is YOLO, but that's something else. So the thing is, what we found, we did this and it didn't work well. It kind of worked, but it worked actually pretty poorly. So I was searching for papers and I found a very obscure paper that improved on the method of using CNNs for coordinate regression. So it used a classifier, but it chopped off the classification layer. And we tried that with an out-of-the-box CNN, and that solution was immediately better than the UNet. So how can this work? So how can we use a classifier to make an image rectangular, which is not what it's supposed to do? Well, you take the classification layer at the end and you chop it off and you just add a new layer on it that does coordinate regression, like That's all. I mean, even a classification just outputs float, right? Then you change the loss you actually train with, because now you don't classify. So, for example, use mean square error. And then you train for normalized coordinates. So the output of your classification is not a classification, but the coordinates of the points. And what is important, the points always have to be in the right order, like always clockwise. So this is the output of my classifier now. And what were the results of this weird experiment? It worked great after we did some hyperparameter search. And ResNext, just for you if you want to try it, perform PEST. It has skip connection. And the weird thing is that the pre-trained classification networks did better. And why is this so weird? Because CNNs are about losing local information, extracting features, and so you can actually do a classification. So the coordinate information should not be present anymore after many CNN layers. But, well, pre-trained networks performed better. The sad thing is the paper I mentioned actually then made the results worse. So I'm not going to quote it here to put some shade on the authors, but it gave us the initial idea. And this method is fast, quick, and it's worked great. So here we see we use something for something that it's not intended to use. In the next chamber I want to show you, which I call the chimeric chamber, we will start taking things apart and putting them together in the way they are not intended. It is a little continuation of our previous story, because once we had this treasure map rectification in place, what happened is suddenly we had images without treasure maps. So ironically, now we needed a classifier. So what would you do? You train a binary classifier. Is there a treasure map? Is there not a treasure map, right? That's the normal solution. The thing is, we were space constrained, so we couldn't use additional networks. Yeah, we just wanted to do everything with one network. But our network, that is actually a classifier, is now a regression network. So how can we use the network that used to be a classifier, but now is a regression network, to do classification? Well, very simple. We just add images where there's no treasure map, and the target coordinates is just zeros. And then we do an epsilon check on the result to say, is this a true or false classification? And we continue training with a regression loss. And two things. This is not a joke. This is a production number. I mean, a binary classifier isn't that hard, but it works with 100% accuracy in production. And the weird thing is, this improved the rectification significantly. This is the weirdest result. Adding images without treasure maps made the regression of the coordinates on the treasure maps better. So, but that's not enough. Let's make it more weird and complicated. Sometimes you have images where there's a partial treasure map. So what do you do then? Wouldn't it be cool? A human knows where the corner of the map is, right? You could place the corners of the map and then cut it out and stretch it, and you get a rectified image where there's a black corner. So how do you train for that? Well, you just add black borders during training. So some of your corners will fall into that black area, and you re-normalize the coordinates, and everything that's in the black corner, in the black borders, gets a value larger than 1. And the partial images will still be correctly rectified, just with a black corner where the corners lie outside. And now comes the kicker. Now we have a second classifier. We check if any coordinate is larger than 1, and then we know if the treasure map is only partially visible, which is great for use cases, because now we can ask the customer, what happens if your pirate shows you only a partially visible treasure map? Yeah, do you leave him on the island, maybe, or not? So, yeah. And at the end, this whole system is what I call a Fiji deep learning Fiji mermaid. If you don't know what a Fiji mermaid is, I encourage you to Google it. They were mummified mermaids you could buy. They were in these chambers of curiosities and all over the world, and they were actually stitched together from monkeys, fish, and various other stuffed animals. They're called Fiji mermaids, and this is what I call this network. It's a deep learning Fiji mermaid. It's a classifier where we chop off the classification layer, where we chop on a coordinate regression, then we add an epsilon check for classification, and then we add some borders to allow for partial rectification. So it's stitched together from various parts that normally shouldn't go together, and well, it works surprisingly well. So that was a nice example, but now, as we all know, real projects can be sad, scary, and data is scarce. So now we enter the world of the Destitute chamber, a world of death and starvation. And that is another task, again, to classify images. And we all know how it is. We never get the data we need, right? So we are starved to death for data. And that's what we had to do. We had to classify documents of a highly sensitive nature. And we were given one training example per class. And the target was to classify over 100 classes. Well, what do you do in this case? Again, the normal solution that you should all know. It's the so-called one-shot classifier, unless you take a big LLM and ask it, of course. That's something we can do now, but that wasn't the case then. That is called a one-shot classifier. What you do is you take a normal CNN, this is ResNet, for example, and you enter the image, let it go all through your network. And here, instead of classifying the output, you just use this output vector, which is like a fingerprint of the image. And then you do that for all your reference images, and you compare the fingerprints of your reference image with your input image. And this can sometimes kind of work. This is a desperate measure, but a very well-known desperate measure. And you just choose the fingerprint which is most similar, and that is your class. So obviously we did that, best practice. And the results were awful. I mean, we just started with 10 classes instead of 100, and we had an accuracy of about 20 or 30%, which is still more than random, so it shows that the principle works, but it's way, way too bad for production. The client required, give us at least 95%. So, okay, you got one image per class, 100 classes, give us 95%. Then you start to get really desperate. How desperate? We had, part of the project was an OCR system. So we had an OCR system flying around. And in an OCR system, you actually use a UNet. Remember the UNet from before? What does a UNet do in OCR? It detects where characters are. So you get a black and white image where the characters are. So, and we had this UNet, it was already there. So what we did is we didn't use the embeddings as before from an actual convolutional network that is supposed to detect images. No, we used the bottleneck of a UNet. A UNet is called UNet because it's a network that's shaped like a U, and the data is first extracted, and then you create an output image. Here, the most interesting information is in the middle, because here is already a black and white image that we don't care about, but the information about the input is here. So ironically, we used a detector for classification. So the UNet, which is actually meant to detect things where they are, now we use for classification. So we again have these embeddings. We compare the fingerprints. How did it work? It worked so well, it should not work that well, but these are production numbers. We get over 99% accuracy in production with that method. So for our 10 initial classes, so that was a big, big win, and kind of cool to pull that off. So you see, you can do, if you're really pressed, you can do a lot with very little. Now, emboldened by those great results of what we can do, we move to higher things. We move to the Transcendent chamber. So let's go into higher realms of higher dimensions and even weirder stuff, and continue with our weird little classifier. Now we need to improve to 150 classes. Well, that's easy, right? We just create more fingerprints and compare them. That's the cool thing about the system. We don't even need to train anything. And we did that. Took us, I don't know, we just added a few the reference images, some JSON files for configuration. That's it. 50 minutes of work to add another 100 classes. Great, right? Well, and suddenly our server startup needed 12 minutes, and each classification took 30 seconds. So how can that be? I mean, you just compare a few vectors, right? So we were, frankly, a bit spooked, to say the least. So we had a closer look. Actually, we didn't check those UNet embeddings. They worked, right? And we know this. We don't write papers. We have to make software work. If it works, better not touch it. Well, we had to touch those UNet embeddings. Turns out bottleneck is not quite the right term for a UNet because it's not an autoencoder. What a UNet does, it blows up the dimension of your input larger and larger and larger by creating more and more, sucking more and more information out of it. This is why it works so well, right? one fingerprint had 4 million activations. We're talking floating point 32. So the 150 classes, just the fingerprints took 3 GB. And we calculated the fingerprints on the fly at server start, so the server took ages. And we only had small GPUs. So a large chunk of our GPU was suddenly filled with fingerprints. You can fit a whole LLM in that space. So that definitely didn't work, and the inference time was way too large for the use case. So again, now this is really mean, right? We have this solution which shouldn't work. You get to work, and right before you win, it's snatched away from you again. So now it's time to bring out the big guns. I was talking to Conrad this morning about how to design a proper slide. This is not how to design a proper slide, but I was told that in Renaissance times, slides used to contain much more text, so I think this is fitting. And I actually made this a bit more complicated because this is something that scares people, right? Big name, the Johnson-Lindenstrauss lemma, a big formula with Greek letters. So this is hard. And I actually added this here for those people who normally don't want to touch this, to take a bit away the fear of reading something like this. Because here is the layman's terms explanation. If you have a very, very high dimensional vector space, so a fingerprint with lots and lots and lots of numbers, 4 million in our case, and this Johnson-Lindenstrauss lemma tells us that there's a matrix, somewhere out there is a matrix that takes those 4 million entries and projects them down to something very small and manageable, say 1,000 entries. And now it's the weird thing, the vectors still have the same distance. This is absolutely not imaginable in 3 dimensions. If I take 2 points in 3 dimensions and map them on a piece of paper, they will often have very different distances afterwards. But the Johnson-Lindenstrauss lemma tells us this is possible. And why should you not be afraid of the math here? I will quickly go through this formula, not so you understand everything, but just to show you that once you get used to the symbols, it's not scary. There are some additions, we know them from school, they work like they used to work, plus, minus. There's a smaller than sign, works as we know it. There's a square, no different, it's just a squared number. And epsilon, this is the first trick, sounds fancy. Epsilon just means small. This is the mathematical way of saying something is very small. So, and if I look at this, an F, a linear map F, is what we call a matrix, or a linear layer in deep learning terms. So it's also not very complicated. It's just a matrix from a big N to a small n. It's a matrix. So this tells us, this weird formula that says, if we change 1 by little epsilon to the left and to the right and multiply the distance of the vectors, it is almost the same as the distance after multiplying. And that's good enough for us, because all we care is about the distance of fingerprints. So this is the most mathematical slide I have. But just to show you, we are used to reading code, and a line of code is read very quickly. Yeah, I can read 20, 30 lines of code by just going through them if I'm used to programming. You just have to read this slower. Just imagine this is 10 lines of code, and go through it bit by bit, and suddenly it loses all its strangeness. Nevertheless, the effect itself is weird, right? We just multiply our fingerprints with something, and then they get smaller, and they still work as fingerprints. The question now is, where do we find such a matrix? This is typical for mathematicians. I guarantee you there's something that has these great properties, and you ask, yeah, okay, how do I get it? Well, that's not what I proved. I just proved it exists. So it tells you that there are unicorns, but not how to catch one. Well, in this case, the solution is ridiculously simple. The matrix that does this is a random matrix. It's absolutely weird. This is something that should not work. There are certain criteria how random and about the randomness, but you just take a random matrix and it works. The thing is, I tested it and it works and was great, and I thought I'd solved it. The thing is, a random matrix large enough now is 8 GB. So I found a solution to get my fingerprint smaller, but the solution was larger than the original solution. So again, thwarted. I mean, it's still interesting in and of itself. But here comes the real kicker. You need a random matrix, but you can make it much, much easier. You only need 1 or a -1 in each row or column, depending if we view it transformed or not. I put it like this on the slide. This is all you need. And now all you need to save is 4 million ones or minus ones, and this is very small. And then either your framework supports what's called a sparse matrix multiplication, so this takes very little memory and is very quick, or, and I leave this exercise to the reader, you can actually do this multiplication just by projections and additions. And now the embeddings take 2 megabytes, and the whole process, once you have the fingerprints, 10 milliseconds. And this is the weirdest part, the accuracy did not change. So I think it's hard to imagine, and it's very weird, but absolutely awesome. Who here knew about the Johnson-Lindenstrauss lemma? I saw some people nodding. 10 people, that's quite a lot. So it's obscure, but it's very, very useful. Okay, emboldened by this, now we will travel out to sea, stormy, dark seas and deep seas, into what I call the Bentic chamber. This is a very little thing. Everybody don't move, don't react. I did some consulting with a very good machine learning team. So they were great guys. They did everything right. They had more money than we, bigger team than me. I wondered what I did consulting there. And the one weird thing when I told them how we work for other customers, where we put multiple models in a single GPU, is that they didn't know you could do that. So I figured, well, if you don't know that's possible, it's really important to know. So everybody don't move, just pretend you knew that you could do it. So I bet a handful of people here didn't know you can load multiple models in a single TensorFlow or PyTorch session into one GPU and then use all the models together. If you didn't know, then just pretend you did. The other thing, the flip side of this is that you can have one model to multiple tasks. Of course, we know this from ChatGPT, right? It can do everything. We just ask it. But technically, it does only one task. It has string input and string output. Here we leverage this string output and input and output to do multiple tasks. But what you can actually do is, if you have one neural network, and we saw that you can chop off things, but you can also sew on things. So what you can do is you take one network and add what we call multiple heads. So it isn't in a neural network then that one layer goes into one next layer. It's just layer on layer on layer. No, the last layer can go into multiple layers, and each of these layers does a different task. This is called having multiple heads, like Hydra from Greek myth. And what you just do, you add a separate output layer for each task and use a different loss. The proper loss. So you can have one layer do regression, you have another layer where you do a classification, maybe you have an output layer that produces a black and white image. You can combine all these and you have multiple losses and you just add them all up and then do a gradient descent. And one network can actually learn to do multiple tasks. Now the experts will say, wait, but there is something called catastrophic forgetting, because networks, when they need to learn multiple tasks, if you train them in sequence, if you train the first task with the first head, it will work. Then you go to the second task with the second head. The problem is now you will erase all knowledge of the previous task. So now it will only know the second task. This is called catastrophic forgetting. And the problem is that one task may have 100,000 data points and the other just 1,000. So it's very imbalanced. So it will focus on the one task and not on the other. And within one task, you may have imbalanced data sets. You might have 1 million cat pictures and only 100 dog pictures. And well, there's a technique to combat all of that. And it's rarely known. And we're in the deep sea, right? So, well, what do we have plenty? Water. So we fixed the problem by flooding. This is a very, very cool paper that is not quoted enough, in my opinion. Do we need zero training loss after achieving zero training error? The obvious answer is yes. Yeah, give us zero loss. This is what we want. And they do something very weird in that paper, something very counterintuitive. If your loss reaches a certain very low level, they limit the loss at that level. So say your loss limit is just 1, just because it's easier. Normally it has more digits. If your loss sinks below 1, you bounce it back above 1. So say you have actually a loss of 0.9, you flip it around and return a loss of 1.1. It's just one line of code, it's in the paper. And the effect is you cannot go below the water level with your loss. But that forces the network to never overfit. It cannot overfit. It wants to specialize more and more and more, but you always push it back. And if you do that with multiple heads, this is what I found out. I don't know if they manage multiple heads in the paper. You can actually force the various parts of the network not to overfit and push away the other knowledge. This is also generally a good regularizer. So if you have overfitting problems, you can just use it for that. And it's incredibly simple. It takes one line of code, this technique, and has great, great, great results. And it's called flooding. And we actually used that back in the day when GPT architectures weren't the premier transformer architectures, but actually a BERT. So we trained our own BERT model, and BERT models you still had to fine-tune for each task. So some simple task maybe you could do, but normally a BERT model had to be fine-tuned. Say you wanted to detect persons in a piece of text, so you had to have text with all persons labeled, and then you could teach BERT to label those persons for you. Classic NLP. The thing is, we were and still are a poor company, and all we could afford was one gaming GPU for our web page for the demo. But I wanted to show multiple BERT applications on one web page. So I had to fine-tune BERT to do multiple tasks at once, and this worked. So basically, we have a BERT which has, I think, currently 3 heads that does 3 tasks. They're all regularized with flooding because the named entity recognition task had hundreds and thousands of examples because there's a nice big data set. And then there was our own grammar task where only had 1,000 examples. And flooding made sure that all the heads separately could learn this. And actually, they are only slightly worse than the training with a single head. So that was pretty impressive, I think. And flooding regularization saved the day. Okay, now further emboldened by all these weird techniques, we can try to lift heavy weights like Atlas did. And now let's see how we can do very heavy and big tasks with very little in what I call the Atlantean chamber. This is a more regular approach. This is actually a bit best practice if you know it. Say you have a very small GPU, but you need a larger batch size. So the problem is you cannot train your model with the batch size you want because there's just not enough RAM for each step. There's something called gradient accumulation, which is implicitly built into every deep learning framework you will ever use. You just use a smaller batch size, and you call your backward step on each training step like you're used to. You calculate the gradients every time, but then you call the optimizer and the zero grad every 32 steps. So basically you keep calculating gradients and gradients and gradients in very small steps. And when you have reached the batch size that you actually want, then you optimize and do one step. And this is, by the way, the reason why you have to call zero grad, because just calling backward in each step adds the old gradients to the new gradients. I didn't know if you knew that. So you can actually do this. So PyTorch, for example, when you call backward, you have the gradients for all your parameters in your neural net. You call backward, the gradients are added to the existing gradients. And that would, if you forget zero grad, then you have old gradients lying around and your training will be weird. And this is why you have to call it manually. But because you call it manually, you can do this little trick. And this is how we managed to train BERT on a 1080 with 8 gigabytes of RAM. We were actually able to train a BERT medium with a batch size of 64. But we literally went to batch size of 1. Which also works. So if you can fit one batch into your GPU, and if you don't know, it's a bit like the story of Prometheus. You, rip out the model's liver bit by bit over the course of the day until you updated it. And then there's another thing. Vector databases are great, right? So you need a big vector database, and you initialize it properly, and you play with the parameters. Well, what if I told you that in very many cases, these lines of code are your vector database. So all you need is, it's nicely formatted. So let's say you need 5 lines of code to build a vector database. So how can this work? We maybe for those who are not too fluent in Torch, what do we do here? We have a query, which you know is your what you look for in your database. Let's say a piece of text, and you just normalize the query. It's normalizing a vector. It's a typical technology. And then we have our embeddings, which are in the vector database. That's why it's sometimes called an embedding database. And you multiply. Again, it's just a multiplication. And top K chooses the best results, and you get the indices of those results. So this is weird. So we multiply a vector and a matrix and take the best performing indices. How can that be useful? Well, it's a bit less math. I told you the last slide was the most math. This is a bit less. This is because similarity search in certain cases is just matrix multiplication. Matrix multiplication is like a batch scalar product, and a scalar product is the same as calculating the cosine. So how can a cosine help in finding things? Well, if two vectors are very similar, they have a very small angle, right? Two vectors that are almost the same lie on top of each other, so they have a small angle. The cosine of a small angle is 1. So if the cosine is near 1, you have a very good match between two vectors. And this is what the normalization did here, because we normalize all our vector, the ones we look for and the ones that are in the query, we get a lot of cosines. And then we just take the biggest cosine values we get, and that way we get the closest documents we have. So this might sound, why would you do that? Well, the reason is because it's fast. Up to 1 million data points, you can do this on your device without having to set up a database connection with all the administrative overhead. So in smaller rare cases where you just need to find something quickly, this will save you a lot of implementation time, a lot of money, and it actually works. We used it in one project where we just only had to classify 500,000 documents. So that is quick when you do this. And no license cost. So let's now come to the last chamber, where everything so far has been weird and very out there. So let's try on our way out to impose some structure on what we do in our work. This is why I call this the formulaic chamber. A very, very simple trick, but still not very common. An LLM doesn't have to talk to you. It talks in text, and text is JSON. So everything you can write as a piece of text can be output by an LLM. And when you tell your LLM to output JSON, XML, or CSV, you can actually use normal code to process that. And if you want to know why this is such a cool trick, I recommend tomorrow's talk, Turn LLMs into Consistent APIs, at 9 o'clock by Peter, who will talk about this topic in depth. What you can also do is, if an LLM creates lots and lots of output and it hallucinates, but sometimes you want to ask it a yes or no question, right? Is this a cat on the image? Or does this document belong to finance? And you just wanted to say yes or no. And then it starts, well, I think this is a finance document because it has the word bank in it or something. And you say, yeah, that's very nice, that's even correct. But how do I parse that? How do I get my structured output? Even if I tell it to say only yes or no, it might ignore me. Well, you can modify the probability of the output of the model. It always creates, when you create tokens, a probability distribution, and you can just modify it. You remove from the probability distribution that which you do not want. And like, for example, Llama even has this built in. If you use Llama on Llama CPP, you can provide a grammar that makes sure that your output is always formatted in the way you want. And a last trick, it's called caching. When you use an LLM and you have the same query, you have here great prompt. It's 2 pages long, but it's perfect. It has all the examples, it describes your task and solves your problem greatly. Well, your LLM will always read the 2 pages. So you have 100,000 queries a day. Those 2 pages will be read every time by your LLM, which will make it slow, which will cost you tokens, which OpenAI, of course, likes. The longer your prompt, the more money they make. Well, especially if you use a local LLM, you have the option to say, well, read the prompt once and cache it. Like, for example, those who program servers, you can cache a database connection. Setting up a database connection is slow relative to the rest of the code, so we pool them and keep them around and reuse them. You can do this with a prompt. And then you just reuse this prompt again and again and again, and you save a lot of time and money. So, I hope this weird collection, I hope everybody found some tidbit. I hope you found it entertaining. And now as we leave the stuffy chamber into a beautiful garden, I hope you enjoy the rest of the conference. I hope it will be just as interesting and you find all the things that you like. And thank you for your attention.
Fun stuff, enlightening stuff, useful stuff. Thank you so much, Christoph. If you got questions to Christoph, he's walking around here, and please feel free to ask. Enjoy the afternoon, and do not forget we are meeting at 6 o'clock for the expo reception over there. Yeah, grab a glass of beer or something like that. And again, at 6:45, also in the expo hall, there's the ML exchange going on. Lots of opportunities just to discuss and to ask some questions to the speakers, to Christoph and to all the other speakers. Thank you very much. See you later.